What's up, everyone? So my name's Rob, and this is a course on an introduction to statistics for the psychological sciences. And today we are going into the topic of null hypothesis significance testing. I'm hoping, so this is a kind of a fresh shift. And what we're going to be doing today is essentially taking a lot of what we've learned so far in the course about normal distributions, about information about how to find what proportion above, what proportion below, what raw score would you need to have to cut off 95% of the population, for example. We're going to leverage that to test hypotheses, right? To be able to more efficiently determine when it's safe to make an inference about a population and when the evidence is not sufficient to make an inference about a population. And so this is going to be, conceptually, I think, a challenging lesson. But when it clicks, I'm hoping it has the potential to really change the way you think about science. And so let's just dive in, and I want to start and talk about a little bit of philosophy of science. And so one common misunderstanding and criticism of science is that, well, scientists kind of think they have proof for everything. And that is absolutely untrue. So when we're using inferential statistics, it is not possible to prove at all. Inferential statistics rely on probability, and there's always a probability that your prediction is going to be incorrect. That's why there's error in prediction. And so it is not possible to prove something with inferential statistics in science. And so another angle at this is kind of from this guy, Karl Popper, who suggested that it's only when we have evidence that we're able to falsify what's not true. And so Karl Popper, he was a critic of classical induction. And he emphasized the importance of empirical falsification. And this is the idea that a theory can never be proved, but it can be falsified. And so the idea is that we have that evidence mounts over time, and each time we have new evidence, it's falsifying what's not true. Right? It's removing what's not true from the pool of possibilities of what is true. But there is never a claim to what is true. We can never really know what's true. We can only falsify what is very likely not to be true. And so let's take, for example, the theory of gravity. Well, we don't know that the theory of gravity is true. It's just a theory. However, at any point in time, someone can come along and say, see this pen? I'm going to throw it up in the air, and I think it'll float. And if they provide that evidence, the theory of gravity would be seriously modified. The fact is that evidence just doesn't exist. Right? You can't be on Earth and throw a pen up and it float. So no one is saying that the theory of gravity is true, but the likelihood that it's false is incredibly low. And we could say the same thing about the theory of evolution, right? The theory of evolution, no one's saying that this is true, but that anyone can provide evidence at any moment in time that would require scientists to modify the theory of evolution to incorporate that some aspect of it has been falsified. But theories, as they develop over time, the theory is the strongest thing we have in science. It is a surmounting level of evidence. And over time, the likelihood that some major discovery is going to be made to completely falsify the theory of gravity or the theory of evolution or the germ theory of disease is quite low. And so while in a purist sense, scientists never can say this is the only truth, they can hone in on a likely truth, but there's always a degree of uncertainty around this. And so this is going to become, I hope, very evident to you in how hypotheses are tested with inferential statistics, how this falsification process works. And so, but now let's talk about another problem for science. And that is the problem that we, even scientists, every person alive feels certain things are right to us. We might feel like opposites attract when the evidence in contrast says that birds of a feather flock together. And so this guy, T.C. Chamberlain, he was a scientist who's a geologist who studied glaciers back in the late 1800s. And he highlighted this problem for empiricism in a kind of with some beautiful language, although it's gender biased, I'll give you that. He said that, the moment a person has a hypothesis, affection for this intellectual offspring kind of comes into the picture. And that as this affection kind of clusters around this hypothesis and this idea that we have, we begin to love it. And we no longer are able to hold it impartially. And so he's highlighting this problem that we become, as humans, we naturally become emotionally involved with any kind of pet theory that we have. And this emotional involvement or affection distorts how we seek out and interpret evidence. And so this highlights how our thoughts and feelings, our motivations, our goals can profoundly distort our ability to see things in a clear, evidence-based way. It's almost as if because we have goals, because we feel certain ways, because we believe certain things, because we have certain moral intuitions, that it's almost like we're seeing the world through rose-colored glasses. Those things distort. We see what we want to. We have confirmation bias. We seek out evidence that confirms what we want to believe. And so, in essence, the flow, like our emotions, our goals, our moral values frequently distort our ability to understand the basic data of experience. And it does so in a way that validates our personal preferences. But we're not after our personal preferences. A scientist is after what the evidence say is fact about experience. And as such, oftentimes science presents us with the fact that it's very likely we're wrong. More often than not, the evidence will not bear out. And a scientist goes based on the evidence. And so it doesn't matter how much you want your theory to be true, how sexy your theory is in terms of its elegance or reasonableness. What matters is the evidence. And oftentimes, as we know, we live in kind of a crazy world, right? Oftentimes, the evidence is in stark contrast to what we want to be true. And so science is humbling in that way, in that the evidence is the arbiter, and we have to take a back seat. We have to be humble about our own brilliance. So, you can see this, not to beat a dead horse here, but you can see this in that, we used to think that the Earth was the center of the universe. And over centuries, we found, well, the Earth actually revolves around the sun. We wanted to believe we were the center of the universe. But the facts didn't bear it out. And then we realized, there's all these other planets that have mountains and valleys, and then we found that, we're just in one solar system. There's actually a much larger galaxy. And in fact, we're in a very insignificant place in this galaxy that we're in. And our galaxy is insignificant in size, in years old, compared to the billions of other galaxies out there. And every step of the way, it was this ability for evidence to inform science, to inform our perspective. And it's been humbling that, to see that we went a few centuries ago from thinking that we were living on a flat world around which everything else revolved and we were the center, to not having any sense of special importance in the overall cosmic drama that we're in. So, that's a little extreme. However, let's talk about null hypothesis significance testing and see if we can bear out how this is working. So, let's start with an example of a real-world situation. How would we test a hypothesis in the courtroom? Well, the first thing that you do is you set up two opposing hypotheses. The first one is called the null hypothesis. And this is what, based on no evidence, our current state of knowledge, what is the provisionally accepted thing that's true? And opposing that null hypothesis is an alternative. And the alternative hypothesis is basically what people typically think of when they think of a hypothesis. This is what the researcher is trying to show, right? They might be, so in a court of law, the prosecution is trying to show that a person is guilty. But when they walk into the courtroom, it's presumed that they're not guilty. So, what is the decision criteria? What is it that we use to determine whether someone's guilty? And Judge Judy doesn't want you to pee on her leg and tell her it's raining. She wrote a book about it. Pick it up if you're interested in learning why you shouldn't pee on her leg. But seriously, what is the decision criteria in court? Well, we presume that people are innocent until proven guilty. Right? Now, the language prove, I think, might be, from a scientific angle, maybe not entirely accurate. Essentially, what we're saying is that you walk into the courtroom innocent, and it is the onus, the burden of proof falls on the prosecution to show beyond a reasonable doubt. That's the decision criteria. That beyond a reasonable doubt, you are likely not innocent. There's never really a claim that you're entirely guilty, right? It's assumed, it's provisionally accepted as true. But you always have the right to an appeal. And at any moment during an appeal process, you can provide evidence to overturn your conviction. And we see the Innocence Project, right, who gathers DNA evidence to exonerate people who were convicted of crimes that they didn't commit, right? And so they provide DNA evidence, which is incredibly strong evidence, to overturn convictions of people who are actually innocent. And so you can see here the court implicit, even though they're using this word prove, implicit in the assumption that you are not innocent is that it's possible to flip a conviction. So why is this the case? Well, our society values letting guilty people go free more than charging innocent people for crimes that they didn't commit. There are other countries that flip this, right? There are other countries where you are presumed guilty on being charged and must provide evidence to support your innocence. But in this country, we have collectively agreed that people will be innocent by default. And it is up to the state or whoever the prosecutor is to provide enough evidence that beyond a reasonable doubt, you are not innocent. Okay. So implicit in this is this beyond a reasonable doubt, right? What is beyond a reasonable doubt? Well, this evidence has to be persuasive enough to overturn the assumption of innocence. And so what happens? So the prosecution provides a bunch of evidence that suggests you're guilty. And if it's enough evidence, then they will reject the null hypothesis that you're not guilty and provisionally favor the alternative hypothesis. If the evidence is not substantial enough, then we would fail to reject the null hypothesis and retain the null hypothesis. So that would mean that you would still be considered innocent. So important to this is that in reality, there's never proving going on, right? We are simply provisionally accepting things as true with the option of being able to overturn that provisional claim in light of new evidence. And so my area is in mindfulness. And one interesting, another piece of statistic Zen, right, is that 2,500 years ago, the historical figure of the Buddha kind of concisely stated the centerpiece of null hypothesis significance testing, in that he said that he was asked, how do people safeguard the truth? And he says, well, you make the conviction that you make the statement that this is my conviction, but you never come to the definite conclusion that only this is true and anything else is wrong, right? So you never stake a claim on the truth, right? You say, my conviction is thus. You say, but I'm always open to the possibility that I could be wrong. So I think this is interesting that 2,500 years ago, this was a centerpiece to this kind of philosophy and used in debate. So, okay, we've described how how this general sense of null hypothesis significance testing occurs in a courtroom, but what are the decision criteria? What is the beyond reasonable doubt in science? Right? Well, in science, and specifically in statistics, right, we want to say that the likelihood that we would get this result due to chance is low. Another way to say that is if we know information about a particular population, say we're dealing with a population of people and we want to assess whether or not our treatment to improve well-being is effective, right? So we set up a null hypothesis that the treatment is not effective. And then we set up an alternative hypothesis that the treatment is effective. In other words, it increases well-being. And we can plot the distribution of what we would expect from a population, a null hypothesis population, that, what is people's well-being in general? What is the population if the null hypothesis is true? If there's no difference between people in our treatment and people in our population. And then we can compare our sample to that population. And the way we do it is we set a criterion, right? And so if there's this shaded region, oops. Okay, so say we have this normal distribution, and this distribution we standardize it, we put it in units of z, and this distribution has a mean, by definition, of z, a population mean of 0, and a standard deviation of 1. And we might, we might say that the alternative hypothesis, or the null hypothesis, is that the treatment is not effective. And then the alternative hypothesis is that the treatment is effective. And the burden of proof is on a scientist to provide evidence that indeed the treatment is effective. And if she does so, we can falsify this null hypothesis and say we will provisionally assume that the treatment is effective. Well, how do we do that? Well, if you remember, we did all these problems where we took a normal distribution, a distribution of z-scores, and we did problems to compute, what proportion of people score above, a z-score of 1.645 or a raw score of some value. And what proportion would be between this and this, right? We did we learned about how we can slice and dice up a normal distribution and understand, proportion above, proportion below, proportion between, that kind of stuff. So we're going to leverage that now in a conceptual way for hypothesis testing. So if we know that the well-being score in a population of people who don't receive treatment, for example, is going to have a mean of 0, and then we give people treatment, and all of a sudden we see that this population has a mean way, way, way far away from the people who didn't get the treatment. Well, the way we falsify the null hypothesis in science, using null hypothesis significance testing, there are other ways to test hypotheses. But is we set a line in the sand, right? And we call this line alpha. Alpha. And what alpha is it's this line in the sand where the likelihood that our sample population belongs to this null hypothesis population is less than 5%. Right? We would expect that if nothing was going on, that if the treatment was not effective, that our sample data would show that the well-being scores of our sample were practically equal to the scores of people who didn't get treatment. But when we collect the data from the people who got treatment, if their scores are much higher than the people who didn't get treatment, well, that would probably increase your confidence that the treatment's doing something. Maybe these people that receive our treatment don't belong to the population of people who didn't get treatment. Maybe they belong to a different population. And that population is people who receive treatment, right? There's something happening to make this mean so much different from the population of people who didn't get treatment. And so whenever we can push this mean so far away from the null hypothesis population mean that it would only occur less than 5% of the time, right? So we're looking at this shaded region here down at the bottom. We call this the region of rejection. And if our mean is so different that you would not get this by chance less than 5% of the time, we say, oh, this is statistically significant. This is the difference between this mean and this mean is so big that it's statistically significant. And then what we do is we say we reject the null in favor of the alternative. Okay. Now, let's look into this region of rejection with a little more specificity. So what's on this slide is if you look it up in your area under the normal curve table, you will see that the z-score that cuts off 5% in the tail is 1.645. Now, this is to test what's known as a directional hypothesis. So here, in this case, we think that our treatment is going to increase well-being scores. And so we're looking for a mean higher than our null hypothesis distribution. But we could easily be looking in the opposite direction. So say, for example, we were looking at depression score, right? Say we were giving a treatment for depression. Well, if that was the case, we would hope that our treatment for depression would influence, sorry, I'm on the wrong slide again. We would hope that our treatment for depression would be reduced in our sample compared to the null hypothesis population. And so in that case, we would be looking at the cutoff of below the mean. So we want this to be 0.05, and this cutoff, since it's a symmetrical distribution, would be minus 1.645. So both of these are examples of directional hypotheses, where we're looking to see is something higher or is something lower? Oftentimes, most of the time, we might not have a specific hypothesis. Sometimes we might think, I don't know if it's going to be higher or lower. I just want to see, is it different? Right? And in that case, you're dealing with something called a non-directional hypothesis, where we split the level of alpha so that 0.025 is in one tail and 0.025 is in the other tail. And so we do this, and we're able to assess empirically if there is enough evidence to suggest that our sample mean is significantly different from our population mean. And we look in both directions for non-directional. So let's look at this example, right? So here we have a null hypothesis that smokers and non-smokers weigh the same amount. And what that would look like is the distributions would be right on top of each other. The black distribution and the blue distribution are right on top of each other. That's what you would expect, right? There's no reason to believe, if you don't have evidence, that smoking is going to influence weight. However, if you go collect the data and it shows that no, in fact, people who smoke weigh significantly less than people who don't smoke, right? Because smoking is an appetite suppressant. If that mean is so different from the population mean of the null hypothesis that there's no difference, then we would say we reject the null hypothesis and suggest that the average weight of smokers is different from the average weight of non-smokers. Okay, so another important thing that should be apparent here is that what we're actually testing isn't the alternative hypothesis. We're testing the null hypothesis. We are determining whether or not the null hypothesis should be retained in the absence of evidence or rejected in the presence of adequate evidence. And that evidence being that 95% of the time this would not occur by chance. Or another way of saying it is 95% of the time that our sample, something's different from them and they don't really belong to the population of people who didn't get treatment. And so the null, we either have enough evidence to falsify it or we don't. When we say something is statistically significant, that means something very specific. It does not mean meaningful, like significant would mean in colloquial use. It means it is a statistical term. It means that we, on the basis of the criteria, which is alpha that we set, we have enough evidence to reject the null in favor of an alternative. So, and again, we're not staking a claim on the truth here. Implicit in this is we're never saying the alternative hypothesis is true. We're saying the null is false. And provisionally we'll hold as true. We'll say that my conviction is that the alternative is true, but we'll never say it's true. And so science is a humble process. Okay, so let's round this up because we're going to transition here into a slightly different path. So we're using, the important thing to kind of bracket this is that we're using inferential statistics here in an attempt to make inferences about our sample to the population that they represent. Now, we can never say that only this is true, or that this is, we can say that this is likely false on the basis of evidence, but we can't say it's true. And as a consequence, we set it up so most of the time we're not in error. But some of the times our statistical inferences are not going to be correct. So let's look at the courtroom situation, and let's examine what this type of error would be. So in a courtroom, most of the time, if a person is convicted, we certainly hope that they're guilty. But there is a chance that we will convict an innocent person. And also, there is a false negative error, right? Where there isn't enough evidence to reject the null hypothesis that they're innocent, and they're actually guilty. And so we let a guilty person off the hook. And so this first type of error, a false positive, is called a type 1 error. The second type of error, a false negative, is a type 2 error. So the important thing to understand here is that what we're comparing is the result of our claim with reality, what's really happening. So here you can see on the left, we've got the defendant's true status, whether they actually in reality are innocent or guilty. And when we cross that with the decision of a jury, what they say is true, most of the time, not guilty people are going to go away innocent. Most of the time, guilty people are going to be shown as guilty. But there are times when mistakes are made. There are errors. And there's this type 1 error in which we allow innocent people to go to jail. We say that that there's sufficient evidence to conclude that they're not innocent when there isn't. And then there is a time when guilty people walk free, right? So we can see that when we cross the possible outcomes that a jury would decide with what's really true, we get this four-square kind of setup. So what is reasonable doubt for a scientist? Well, the scientist is in control of that reasonable doubt level. And you can think of that as the alpha level, right? The alpha level, in fact, is the probability that you are making a type 1 error. It is the probability of rejecting the null hypothesis when in fact the null hypothesis is true in reality. And so we could set alpha to be really, really small, and that would make it so our burden of proof is harder. It's more difficult for us to show that someone is guilty, but whenever we do, we're much more confident in it. We're confident that we didn't make an error. Or we can make it easier. We could lower or increase alpha and make it so it's easier to show that someone is not innocent, but we have less confidence in that being true. So alpha kind of sets the standard of evidence. And so a higher type 1 error rate means it's easier to reject the null when it's true. And a smaller type 1 error rate, or alpha, means that it's more difficult to detect when it's true. But whenever we do, we're more confident in it. Okay. So In science, it's the same principle. We have a type 1 error, which is when an effect in our sample doesn't exist in the population, that the null hypothesis population. And then there's a type 2 error, a false negative. And this is when you find an effect in your sample that does not occur in the population. So let's think about this just for a moment here. So we have control over it. Think about companies that manufacture smoke alarms. Okay, so you have a smoke detector in your house. Now, the company controls the sensitivity level, right, to smoke. So, in your opinion, would you rather have a smoke detector that will go off at the slightest detection of smoke? And so you're in the kitchen, you're cooking a steak or something, and the smoke alarm's going off every time. Or would you make it so that that it needs to be much more certain about the smoke, but there's a chance it won't go off when there's a smaller fire? You see, the smoke detector company has to determine what an appropriate criterion is to go off, for that alarm to go off. In the same way, a scientist has to set that same criterion. It has to determine when, I mean, we want to have confidence that there is a fire, but we also don't want it to be so insensitive that it doesn't detect smaller fires, right? So we have to estimate what is that criterion. In science, the default alpha value that is acceptable for to state that you have sufficient evidence for a finding is 0.05. But that can vary, right? In certain circumstances, it might be appropriate to use an alpha level of 0.10. Or it might be appropriate to use an alpha level of 0.01. Those are, it's common to use an alpha of 0.01. So we can break this down in science, and what we do here is the same table as we had before, right, with the courtroom, but what we're looking at is what is actually true in reality on the left, and what our statistical test tells us. Right? So we could conduct a statistical test and it can be true, and most of the time it will be, but there is always the probability that it is false. And so we can see that it's possible for us, sometimes we'll get a false positive, and our statistical test will say, hey, there's a significant difference between the people in your treatment and the people who didn't get your treatment, when in fact there isn't, right? It's a false positive. You're saying that there's enough criterion to reject the null hypothesis, when in fact the null hypothesis is true. Alternatively, there's a type 2 error. We may fail to detect a difference. We may say, hey, the treatment didn't work. Our treatment wasn't effective. But in fact, it actually was, right? And so we are in the business of trying to minimize being incorrect. However, there is the probability of a type 1 error and a type 2 error are diametrically opposed. As you reduce the probability of committing a type 1 error, you increase the probability of committing a type 2 error. And as you reduce the ability of creating a type 1 error, you increase the ability of creating a type 2 error, right? So there's a tension between these two errors, and it's up to the scientist to find the appropriate balance point given their circumstance. Okay. So let's walk through an example of what these errors in hypothesis testing look like. So suppose you wake up, you're at home, and you wake up in the middle of the night, and in your mind, you are trying to predict whether or not there's a fire in the house, right? You think you might smell smoke. And you need to determine whether your mind's playing tricks on you or if you need to get up and leave the house because there's a fire. As any good scientist would do, you set up the following opposing hypotheses. The null hypothesis, the default, is that the house is not going to be on fire. The alternative hypothesis is that your house is on fire. And so what you are doing as an intuitive scientist here is you're trying to assess whether or not you have sufficient evidence to falsify the hypothesis that there's nothing going on, that the house is not on fire. So we set up these alternative hypotheses, and suppose in reality, right, what's really happening is that your house is not actually on fire. Well, what would it mean if you fail to reject the null hypothesis? Well, in that case, you think there's no fire, and you go back to sleep in safety, right? You don't reject the null. You presume, the house isn't on fire, right? And in that sense, if your house is not actually on fire, you're correct. And so this is an example of our statistical test being correct. So the probability of correctly retaining or failing to reject the null is 1 minus alpha. So if we just set alpha as the default level of 0.05, that means that 95% of the time this is going to be the case. So let's say in reality, the house is not on fire. And what would it mean if you thought, oh, there's sufficient evidence that there's smoke, right? Well, if you failed to reject the null hypothesis, or if you rejected the null hypothesis, you said, oh, there is a fire, what would it mean? Well, it means you would think that your house is on fire, but there's not actually a fire in reality. And so you'd be out on the streets in your bathrobe. This is a type 1 error. This is a false positive. This is whenever you are rejecting the null hypothesis when actually the null hypothesis should have been retained, right? And so the probability of committing a type 1 error is alpha, right? Alpha is the probability that you are making a false positive. Okay, so now let's flip what's actually going on in reality. So we keep our null and alternative hypotheses the same, but now we're going to say that the house is on fire. In reality, your house is on fire. What would it mean if you reject the null? Well, if you are laying in bed and you say, oh, I think there's a fire, and there really is one, well, you would escape the fire, right? You think your house is on fire, and in reality, your house is on fire, so you would escape the disaster, right? This is an example of our statistical test being correct, right? The statistical test in your head of determining whether or not there is a fire, right? You say there is when there is one. And so this is correct. The probability of correctly rejecting the null hypothesis is 1 minus beta. So we will, in a subsequent lecture, go over the concept of statistical power in more detail. But for now, it's important to point out that 1 minus beta is statistical power. It's the probability of correctly rejecting a null hypothesis when indeed that null hypothesis should be rejected. So what is the fourth and final example here? Well, we have our null and alternative hypothesis. In reality, the house is on fire. what would it mean if you failed to reject the null? If you thought that that there's no fire, when in fact, in reality, your house is on fire, this would be a disaster, right? Because you would not think that your house is on fire when it is. Your statistical test said, oh, house isn't on fire, but it's burning to the ground. This is a horrible disaster. We do not want this to happen. This is a type 2 error. And so a type 2 error is a false negative. It's saying that, nothing's going on. There's no significant effect here, when in fact there is, right? It's saying my treatment program that I've developed for depression isn't effective, when in reality it is, and it could be used to help people, right? So this is a false negative. The probability of a type 2 error is failing to reject the null hypothesis when it should be rejected. And the probability of committing a type 2 error is beta. So here we can line up all of these possibilities in a table and see what their probabilities are. Now, we can't directly compute beta, but we know that beta is related and diametrically opposed to alpha, and we set alpha. So let's just walk through another example. I know this can be conceptually challenging. There's a lot of new terms and language, and we're using some of the prior freshly learned concepts about normal distributions and trying to kind of put all these parts together. So let's use another example. Just think, we'll talk about type 1 and type 2 errors. Think about what it would mean. What would it mean if you took a pregnancy test, for example? And what would a false positive mean? Well, a false positive would mean that the test tells you you're pregnant and you're really not. And what would you feel? You'd probably be freaked out, or you'd be incredibly happy, but be let down, right? Depending on what your motivation is. Well, what's a false negative? A false negative is you take the test, you're pregnant, and the test told you that you're not pregnant. What would that, think about how that would feel. What would the consequence be there? All right, and now you need to determine which is more important to protect against. Is it more important to make a pregnancy test that is without question certain that it is telling you you're pregnant when you are? Or, right, so but you see, like, if we make the test require a higher standard of evidence to determine pregnancy, then we're naturally making it so that there's a higher rate of false negatives, right? If the test requires such a high level of evidence, then sometimes people might not detect weaker levels of hormones or something, and the likelihood that a false negative is going to happen is going to be increased. At the same time, if we say, oh no, we want it to be real easy, right? That the test doesn't require that much evidence to say that you're pregnant. Well, then there's going to be a lot of people who have a type 1 error, who are told you're pregnant when they're not, right? And so think about this. Let's apply this to a real world example. Think of what would you want in a coronavirus test? Would you want it to rapidly tell you that you might have coronavirus, but it be less confident? It might be an error, but it will always tell you if you do have it? Or would you want a coronavirus test that has a super high standard of evidence, and it will always be correct, or most of the time, a high probability of being correct when you do have coronavirus, but sometimes it might not pick up cases. You see, the context matters, right? And that's what's important to understand. There is a tension between type 1 and type 2 error. And I would argue that it would probably be safer for society for us to be more willing to make a false negative than a false positive, right? Even if, I mean, there's going to be a handful of people who get a positive coronavirus test and are asked to quarantine, but we're going to get them all, right? And people who have it are going to quarantine. Some people are going to have to quarantine, and they don't really have it. But you see how this works, right? The tension between false positive and false negative depends on the context. And the way we determine what is going to dictate false positive versus false negative is how we set our alpha. So if we want to reduce the probability of a type 1 error, we reduce the alpha level. We might set it at 0.01, which would mean that only 1% of the time are we going to make a false positive. If we wanted to favor a false negative over a false positive, we would make it easier on ourselves to reach that criterion of statistical significance. So 5% of the time we might make an error, but we're reducing the probability of making a false negative, of not saying that there's an effect when there is one. Okay, so, I mean, again, we can look at our slide here, and we have this null hypothesis distribution, right? And we want to compare our sample to it. And so I'm going to try to reframe what we went over at the beginning of this class, where we're comparing a sample distribution to the null hypothesis distribution. And so we can see from this figure that we set this arbitrary threshold, this line in the sand here, right, is our alpha, right? And alpha, if we set alpha to 0.05, that means 5% of that we're finding the z-score that cuts off 0.05% in the upper tail. And so it's very unlikely that you would just randomly get a result you would get at random, you would pick a result, a combination of people in your sample that had a result, a mean that extreme. 95% of the time, that wouldn't happen. Only 5% of the time would it just be random error that caused the mean to be that different. And so we have a situation here where we're saying that 5% of the time we will be wrong. 5% of the time we just randomly selected a group of people who were significantly higher on this mean. And it was just sheer random error. It has nothing to do with our treatment or something like that. But 95% of the time, it will have something to do with the treatment. 95% of the time, we're saying this population, the mean of our sample is so different from this null hypothesis population that they don't belong to the same population. 95% of the time, that will be the case. 5% of the time, it won't be, and it will be a type 1 error, right? And so, in essence, what we are demonstrating here is we're collecting data on some sample to see if it's different from the population that they represent. I hope this is a very conceptually challenging lecture. I hope you've gotten some insight into how null hypothesis significance testing works, how we scientists don't make claims about what is true, but they falsify. And I hope you can see, and we'll continue learning about these concepts as we move on and apply them. But for now, I hope you can see conceptually how we're able to leverage the standard normal distribution as a way to determine when it is appropriate to falsify a null hypothesis and when it isn't, and the type of errors that we can make in our prediction from a statistical test. Okay, well, thank you guys for listening, and I hope you have a great remainder of your day. Later.